Because from the energy point of view, 4s needs low energy to occupy less than 3d. And because electron prefer to occupy lower energy levels, so the electron here prefer to occupy 4s before 3d. After 4s fill, 3d will fill after. Okay. Effective nuclear charge. The reason for differences in energy for 2s and 2p subjects, for example, is effective nuclear charge Z. Effective nuclear charge Z is the nuclear charge experienced by the outmost electron. Explains why energy of second of 2s is lower than energy of 2p. Then increases across a period onto incomplete shielding by inner electrons. Estimate Z by the number of inner electrons. Charge filled by 2s electron in lithium, for example, it's Z equals 3 to 2, 3 minus 2 equals 1. With respect to beryllium, Z equals 4 minus 2 equals 2, and for boron, Z equals 5 minus 2 equals 3, and so on. Writing atomic electron configuration, two ways of writing configuration. One is called the spectroscopic notation. In the spectroscopic notation, for each atomic number equals 1, so we can express this way. 1s subscript superscript 1. Superscript 1 determine or characterize the number of electrons, and this one is the left side of S is value of n, and S itself is the value of L. Writing atomic electron configuration, two ways, also other ways, orbital box notation. We can put this electron in a box. One of them, in this box, one electron, its direction is up arrow and the other one is down arrow, determine negative half and positive value which is related to this big quantum number here. One electron has n equals 1 and n equals 0, so m equals 0 and ms plus half. Other electron, the same value except ms equals minus half. See toolbox for electron configuration tool here. Lithium, for example, its group is 1a, atomic number is 3, its electronic configuration according to this electrons is 1s2 and 2s1, so the total electrons here is 3. This way for expression, other way for expression by using box. Beryllium, for example, group 2a, atomic number is 4, its electronic configuration is 1s2 and 2s2, and 4 electrons as max, electron as total, okay? And boron group 3a, atomic number is 5, of course 1s2, 2s2, 2bx1, this 5 total electrons. And carbon, for example, some of the members of group 4a, atomic number is 6, and 1s2, 2s2, 2bx1, and 2xy1. This is 6 total electrons here. We see for the first time Hans rule. What's Hans rule? Hans says that when we place electron in a set of orbitals having the same energy, we place them singly as long as possible. Why? Because from the energy point of view, electron prefer to be single rather than occupying, because single is easy for him from the energy point of view. It doesn't suffer more. But if he occupies the other one with direction positive half momentum and negative half, so the repulsion force between each other is very difficult. So we prefer the electron itself from the nature and energy point of view, prefer to occupy single. And after fill everything singly, occupying from the beginning. We will see this. Nitrogen, group 5a, nitrogen represents some of the elements of group 5a. Atomic number is 7, 1s2, 2s2, 2b3, 7 total electrons. And oxygen group 6a, one from the members of group 6a, atomic number is 8, 1s2, 2s2, 2b4. Here we will find 4. 2b will be filled singly at the beginning, and after finishing the single state, will refill 2bx. Fluorine group 7a, atomic number is 9, 1s2, 2s2, 2b5, 9 total electrons. And neon, which is inert gas, group 8a, sometimes you can say group 0. Atomic number is 10, 1s2, 2b, 2s2, and 2b6. So 10 total electrons. Note that we have reached the end of the second barrel, and we are going after that through sodium to the third, beginning of the third barrel. And the second shell is 4. Electron configuration of B block elements. Sodium, for example, which contains 11 electrons on the side, group 1a, atomic number is 11, and its electron configuration is 2b6 and 3s1, or neon core plus 3s1. Neon 3s1, it is another expression for representing the configuration. It uses rare gas notation. begin a new pair. It's a second pair. All group 1A elements have core NS power 1 configurations. Aluminum group 3A, atomic number is 13, 1 is 2, 2 is 2, 2B6, 3 is 2, 3B1. You can represent it other way, you can say neon 3 is 2, 3B1. All group 3A elements have core NS2 and B1 configuration where N is the periodic number. Phosphorus group 5A, atomic number is 15, the same. All group 5A elements have core NS2 and B3 configuration where N is the periodic number. Calcium group 2A, atomic number is 20, 1 is 2, 2 is 2, 2B6, 3 is 2, 3B6, 4 is 2. You can express this configuration as a way by saying argon 4 is 2. All group 2A elements have core NS2 configurations where N is the periodic number. Relationship of electron configuration and region of the periodic table. We can find here 4 colors. The gray one is representing S block elements, the orange one representing B block elements, and the green one D block elements, and the violet one F block elements. As I told before, gray elements in S block, all of them are metal, the orange one, all of them are non-metal, the green one which is present in between is metalloid, and this violet one is related to metalloid but another F block element rather than D block element. Transition metals, all 4 spherical elements have the configuration argon NSX time N-1 D power Y, and so are D block elements like chromium, like iron, like carbon. Transition elements configuration. The problem with transition elements here is the filling of 3D and 4S. 3D orbits used for scandium to zinc. Lanthanides and actinides. All these elements have the configuration core NSX N-1 dy and N-2 Fc. And so are F block elements like cerium, like uranium. Lanthanide elements configuration 4F orbitals used for selenium, Lu, and 5F for thorium and Lr table 2. Ion configuration. In case of ion here, we are going to lose or gain some elements inside the atom. For example, if you are dealing with sodium, sodium contains 11 electrons present in the shell, 1 electron is outermost shell. Of course, sodium as an atom tends to lose 1 electron from the outermost shell to be positive ion, to be in a positive, and its configuration in this case is 10 electrons. Let us see here what's happening. If chlorine with 17 electrons present inside the atom, if it wants to react, he has 7 electrons outermost shell, so he tends to gain electron to complete its outermost shell with A. So its electron configuration will be 18. So some atoms tends to lose and some atoms tends to gain. Let's see here. To form a cation, what's cation? Cation is the atom which tends to lose. To form a cation from elements, remove 1 or more electrons from subshell of highest energy or the outermost shell zone 4. So phosphorus, for example, is neon with 10, 3 is 2, 3 is 3. So minus 3 electron. Minus 3 electron here means that this is phosphorus atom tends to lose 3 electrons from the outermost shell to become, instead of phosphorus as an atom, phosphorus as an ion. After losing 3 electrons from the outermost shell and convert to phosphorus ion with new electron configuration, neon 3s2 3b0. Instead of 3b3, became 3b0, where 3 electron he has lost it during the reaction. Okay. Ion configuration also for transition metal. Transition metal has a lot of transition, a lot of oxidation state, a lot of stage of lose of electron. For example, iron can lose 2 electrons, some days 3 electrons, according to the reaction he's dealing with. For transition metals, remove NS electrons and then N-1 electrons. For example, iron, its configuration is argon for 2,3d6, loses 2 electrons to become iron plus 2. You can mention as ferrous. Argon 4 is 0,3d6. Ion configuration, how do we know the configuration of ions? Determines the magnetic properties of ions. Ions with unpaired electrons are paramagnetic. without unpaired electrons is diamagnetic.
Thanks.
Help with